Hi, my name is Manish Gupta, and in this video, I'm going to talk about LayoutLMv2, multimodal pre-training for visually rich document understanding. So let's start by asking this question as to what is this visually rich document understanding? So the broad field essentially aims at analyzing scanned or digital born business documents, which could be images of invoices, forms in PDF format, etc., where structured information can be automatically extracted and organized for several downstream business applications. It basically involves joint modeling and joint processing of the textual, visual, and layout information, all three together. Right? For example, what you see here is a document, right? And this basically comes from this data set, FUNSD, form understanding in noisy scan documents. This dataset contains 199 such scanned forms with 9,700 plus semantic entities marked, covering 31,000 plus words. Okay. And the main goal here is to be able to classify each of these semantic entities into either the question part or the answer part or the header part or the other part, right? Any of those four types. The link for the dataset is right here. You can go look at this dataset. Right? I'll talk about more such other data sets which are related to visually rich document understanding. For example, there's this data set called as consolidated receipt data set for post OCR parsing. Right. This data set contains actually 1,000 such receipts, as you see here. Each receipt actually comes with a photo and a list of OCR annotations, optical character recognition based annotations. So for example, black pepper meatball are actually recognized here with their rectangular boxes, right? And what you also have is essentially one of the 30 categories which are marked with each of those boxes, each of those sort of entities that have been labeled by OCR, right? So these 30 fields basically include things like this: name of the menu, which is essentially this one, identification number of menu, unit, price, quantity, discounted price, and so on. So there are like 30 fields, 30 such fields under 4 different categories. And of course, the idea is that, hey, given a new receipt, can you actually find these fields automatically? Right? Um, Here is another data set. This is also based on scanned receipts of this format, right? From Starbucks, for example, right? And the idea is that you have to extract information from these scanned receipts: company, date, address, or total, right? And the data set actually contains around 1,000 samples split across try and test. Here is yet another data set about non-disclosure agreements, NDA documents, right? And the idea is that you have about 500 plus such NDA documents, and you must extract 4 interesting fields from those NDA documents: party, which could be an organization or a person; jurisdiction, which is basically a location; effective date, which is a date; and term, which is a duration. Right. So essentially, some of those things have been highlighted here, like the party being highlighted here, or jurisdiction being highlighted here, or effective date being highlighted there. Yeah. Here is yet another visually rich document understanding task. This is called RVL-CDIP task, and it basically contains images of different types of documents, specifically 16 different types of documents and 25,000 images per class, which basically amounts to about 400,000 grayscale such images. And of course, the idea is to be able to look at these images and classify them into these 16 different classes. Text and layout information can be extracted using, let's say, Microsoft OCR. Here is yet another very interesting visually rich document understanding task. Given this image and this question, mention the zip code written. Can you come up with an answer of that kind, right? Which is of course parsable from here. Okay. So there are 50,000 such questions in this DocVQA dataset coming from IIIT Hyderabad, right? You can look at the dataset in the paper there, right? 12,000 pages across 50,000 such questions, 12,000 scanned pages, of course. And the dataset is in a triple format. So there's a page image, there are questions, and then there are answers. And you could use Microsoft Read API to extract the text along with the bounding box information. Yeah. So these are all interesting visual rich document understanding tasks. Clearly, for such tasks, you need to process text, image, and layout jointly, right? And therefore, you need a new architecture, which is where LayoutLMv2 fits in. Okay. So of course, it must be embedding each of these three things separately. So let's talk about how does LayoutLMv2, the architecture, actually processes text, image, and layout. Right. So text embedding. Okay. So you basically take, of course, you do OCR on the document, input document, and you tokenize that OCR text. and assign it a particular segment. So for most use cases, and even for pre-training of LayoutLMv2, they only had one segment A, called as the A segment. Okay. You also add CLS token in the beginning of the sequence and the SEP token whenever your segment ends. Right? You can also add pad tokens at the end so that overall the sequence length is L, max sequence length is L. Okay. So thus the text part is basically consisting of three things: token embedding, right, for the particular token, right? Then there is a one dimension. So there's the token embedding that you see, right? There's a one-dimensional position embedding. So specifying the position of the particular token in the text part, right? And then there is a segment embedding. Well, there is also this two-dimensional position embedding. We'll talk about it slightly later. Okay, hold on for that. So you take a document, do OCR on it, and essentially you take these lines and they give you tokens as well as positions, and you encode them using the text embedding, using the three parts as mentioned here. The text embedding part is initialized using UniLMv2. It follows the same architecture as well as the initial weights, right? UniLMv2. Yeah. Now, how about the visual part? So, well, you have taken the document and we have already talked about the text part. Now, let's talk about the visual part, right? So, you take the document, resize it to 224 cross 224, right? You give it as input to a visual encoder, which basically in this case is ResNext FPN. And which follows a mask RCNN backbone. And that one, it's more like a CNN, some CNN, right? Which basically gives you a 7x7 output, of course, with some depth to it. So, but then the width and the height of that output are 7x7, leading to 49 visual words in that census. Okay. Now, words and text, visual words and text words are in different spaces. So as to map them together, you apply a linear projection layer so that they basically map to the same embedding space. Okay. So therefore, your overall image embedding now is going to be essentially a projection of the visual token embedding plus the one-dimensional position encoding plus the segment encoding. So remember, in text part also you used a one-dimensional position encoding. You basically share the same weights. So essentially, the same values are essentially used for the one-dimensional position encoding here as well. And for the segment encoding, well, in the text part, you use A and B. Here you use C. That's all, right? Otherwise, you have three parts to the visual encoding part as well. The projection of the visual token, the segment encoding, and also the position encoding, one-dimensional position encoding. Now, third, let's talk about the layout embedding. So how do you encode the layout part, right? So whether it is a text box or a visual box, essentially, you want to encode their layout as well. So the spatial layout is essentially encoded in terms of the boxes, the bounding boxes from OCR. So the coordinates of those boxes are discretized from 0 to 1000, and then you have a two-dimensional position encoding. So two-dimensional position encoding, which tries to embed the x-axis features versus y-axis features. For every bounding box, you actually note down 6 things: x-min, x-max, y-min, y-max, and width and height. Okay. So unlike typical RCNN kind of models, which basically use a 4-dimensional representation for every box, these guys use 6-dimensional representation for more redundancy, right? And then the overall layout embedding is basically, which is this one, the 2-dimensional position embedding is basically an encoding for every box, whether it is a visual box or a text box, right? And it encodes, it concatenates the embedding for the x dimensions versus the y dimension features. Okay. Of course, for the padding tokens, essentially, you have a special box initialized with all, or rather set to all zeros, right? And this box is basically used for all kinds of tokens, like the CLS token or the separator token, or also the pad token in general, if there are padding tokens in your text part. So now that we understood how the text, visual, as well as layout encoding are done, how is LayoutLMv2 pre-trained? Okay, so this is the input, and of course, LayoutLMv2 is also a transformer model. So there are going to be several transformer encoder layers. However, in this pre-training, there are two important aspects. One is the transformer layers with this spatial-aware self-attention mechanism and pre-training tasks. We'll talk about pre-training tasks in the next slide, but let's talk about this small architecture difference, which has spatial-aware self-attention mechanism. Okay. So recall from your basics of transformers that there is a self-attention mechanism, there are queries, keys, values, and then there is QK transpose, and you do, normalize that, take a softmax, and then multiply by values, right? So you'll do the same thing here. However, rather than just doing QK transpose, you would basically do something like this. Yeah. So this is a vanilla transformer. This is a vanilla transformer, and this is how the transformer works in a layout LMV2 kind of a model, right? The right side. Why do you want to do this? You want to do this because you want to model the semantic relative position as well as the spatial relative position of various boxes, right? So while you would do just the alpha ij as the attention weights, you of course retain those, but you have three extra terms in this alpha ij. Okay, one which captures the spatial relative position j minus I, where j and I are indexes, right? And then you also encode xj minus xi and yj minus yi. So both the semantic and spatial relative positions are encoded. If you notice here, there's no absolute positions being encoded. It's all relative. So if xi, so here you might be wondering what are those xi's and xj's. So given any particular box, well, xi yi is the top left corner of the ith bounding box. So if you look at the ith token, you look at the bounding box for that, whether it's a visual box or a text box, well, you would basically have the top left corner of that box, and that's xi yi. Okay. So that's how basically you encode you encode spatial information and make it spatial aware self-attention. Well, they are encoded as biases so as to avoid too many parameters. So you just basically add small little bias terms to the overall alpha ij vector. That's that. Now, that's the difference in terms of how the self-attention works. However, how does the pre-training happen? So the pre-training happens using three tasks here, three pre-training tasks, MVLM, TIA, and TIM, right? We'll talk about all of these three in detail. Okay. The pre-training is done using a large dataset, 11 million scanned documents in IIT-CDIP dataset. Basically, the text part is actually obtained using TextOCR using the Microsoft Read API. Right? LayoutLMv2 actually has pre-trained two different models, base version and the large version. Base model is 12 layers, large version is 24 layers. Base one has 200 million parameters, large one has 426 million parameters, almost double the size. Yeah. So now let's talk about the three tasks, MVLM, TIA, and TIM, right? So MVLM is basically, as you could imagine, is masked language modeling, but then here it is masked visual language modeling, okay? So the way this thing works is that you mask out text, and then at the same time, you also mask out the image regions from which this OCR text was obtained, right? So you mask out that particular thing also before feeding the image to the visual encoder part, okay? So but then you don't mask out the layout information. So you retain the information about the box. So you're trying to basically guess the words which were there in this box based on the other words which are not masked out and the layout information of this particular word. Okay. You of course use cross entropy loss with respect to the reconstructed words, and for masking you use the same kind of masking ratio as bird, like 15% of the words are masked and 80% are are actually masked, 10% are remaining unchanged, and the remaining 10% you change it with some random word and so on. Okay. There are two other tasks, pre-training tasks, which are done, TIA and TIM. So TIA is text image alignment. So the idea is that randomly you pick 15% of the token lines. Okay. So you take 15% of the lines, okay, not words, lines this time, and you cover them. Basically you blacken them out, right? And they're called as covered regions. Remember, these covered regions are different from the masked regions, masked image regions in the previous task, right? And then at the output, you have to decide whether it was covered or not, whether it was covered or not. So, so when, of course, these two things can conflict with each other, the MVLM and TIA. And whenever there is a conflict, you basically say that TIA losses of the mask tokens are not going to be taken into account while you compute the overall loss. Okay, that's that. So three pre-training objectives are actually shown here. The MVLM that we already discussed, the TIA that we already discussed, and the third one is the simple one, text image matching. Here, the idea is that the CLS token is actually used to identify if the image that you passed and the text that you passed are essentially relevant to each other or not. So to predict whether the image and text are from the same document page or not. Right? Positive examples are pretty simple. They are regular inputs. But for negative examples, essentially, the way they are obtained is that in 15% image cases, you actually replace them by a random image from the dataset, and remaining 5% cases, and the other 5% cases, you drop the image completely, right? So the TIA target labels are all set to covered in negative examples. So you will basically say for negative examples, all TIAs are covered, right? Now, clearly here, you have to basically just use CLS token to figure out whether the text and image match with each other or not. So you just use binary cross entropy loss. So thus, there are three different interesting pre-training objectives besides the spatial-aware self-attention mechanism. Okay. How is this model fine-tuned? Well, in this paper, the authors actually experimented with six different tasks. Four of them are of document image classification. Four of them are of the sequential labeling kind, right? The four data sets that I talked about in the beginning, well, they modeled them as sequential labeling tasks, right? And they try to therefore do token level classification to predict the BIO sequential labeling associated with the tokens in those documents. Okay. One of those tasks is document image classification. Remember the 16 different classes? Well, so you use just the CLS token, and essentially you also combine it with pooled visual token representation. So you take all the visual tokens, right? 49 visual tokens, right? You take the visual encoding and also the encoding. So you can call it the pre-transformer encoding, right? And you also take the encoding from the top of the last layer of LayoutLMv2, right? And you could call it the post-encoder encoding, right? Post-encoder features. So you take the CLS token, the post-encoder image features, pooled image features, right? And the pre-encoding visual features, pooled visual features, and you combine these all three to basically predict the one of the 16 classes, right? One of the tasks is basically visual question answering task. So here, the input is going to be the question tokens, the context tokens, and the visual tokens. So, and you assign them into three different classes segments, A, B, and C, and essentially, you ask the model so as to be able to predict the right answer. Okay, so you optionally, while you're fine tuning on the DocVQA data set, you can actually optionally also first fine tune using question generation data set, so that because it's a similar task, it's sort of like doing task specific fine tuning or task specific pre-training, as you may like to call it. Okay. Well, these are the statistics of these different data sets. As we discussed, some of these data sets are pretty large, while some of them are pretty small. And some of the data sets have large number of classes, while some of them have small number of classes. Okay. Now, how does this model perform? So, of course, we'll talk about these four different sequence labeling tasks first. And in LayoutLM, of course, you are combining so we're comparing them with respect to various baselines, comparing LayoutLMv2 models with multiple baselines, the standard transformer-based baselines, which don't care about layout at all, right? And also LayoutLM, which is a precursor to the LayoutLMv2 model. Okay? In fact, I did not talk about LayoutLM, but the way it differs from LayoutLMv2 is as follows. Visual information in LayoutLM is actually used only in the fine-tuning stage. But of course, as we observed, visual information is crucial in the pre-training stage itself in LayoutLMv2, right? In LayoutLM, absolute 2D position embeddings are used. But in LayoutLMv2, of course, relative 2D position embeddings are used. Right? In LayoutLM, only MVLM is used as a pre-training task. But in LayoutLMv2, you actually use MVLM, TIA, and TIM, all three. Right? Okay. So clearly you observe that across all the four data sets, these are entity level F1 scores, and you observe that yes, LayoutLMv2 large is really, really nice. And it's not just nice compared to these standard baselines, but actually it's nice compared to all the state-of-the-art models for these four tasks. Okay. Now here are the results that you see, classification accuracy on the RVL-CDIP data set, right? And again, you observe that in the 16 class classification classification task, well, you obtain super high accuracies, 95.64% using LayoutLMv2, which is state of the art, clearly. Yeah. This is another, the last task, the document visual question answering task. Remember the one where you have like 50,000 questions, right? Here, again, you observe that LayoutLMv2 large, along with question generation based, initial training, gives you the best results compared to all the other previous models. These results have been computed using a variant of edit distance. It's called average normalized Levenshtein similarity. So that's how basically these results have been computed. LayoutLM v2 actually has so many interesting aspects to it, right? So essentially, there is there is this MVLM, TIA, TIM, and so on. So there are so many aspects, right? And people observed that each of these aspects is very, very crucial. By removing individually one aspect at a time, you observe that each of those aspects, if you add, let's say, the MVLM, if you essentially have the spatial kind of attention-based modeling, and you add MVLM, you add TIA, you add TIM, and so on. You add each of those aspects one by one, and you see that the accuracy keeps improving. basically saying that each aspect of the architecture is super important and crucial. Yeah. In summary, let me quickly conclude this video by saying that, hey, LayoutLMv2 is an awesome model which jointly encodes text, image, and layout all three together. It does so by using a transformer-based architecture clearly, but with spatial-aware self-attention mechanism and two-dimensional relative position embeddings. Right? At pretraining time, essentially, it follows three different pretraining objectives: MVLM, which is masked visual language modeling, right? TIA, text image alignment, and text image matching, text image matching, right? It has been observed to show state-of-the-art results on several visual rich document understanding, right? Across all of those tasks, it has moved the state-of-the-art by several points, right? Taking them to practically usable accuracy levels, right? More details and description about LayoutLMv2 can be obtained by following that link. Okay? Thanks so much. Hopefully you liked the video. Thanks for watching. Here is my LinkedIn to connect with me, and here is my homepage to know more about my research.